Hello friends, I welcome you in lecture number 7 on higher order PDEs. In previous lecture, we have seen that how to obtain the general solution of this type of homogeneous linear PDE with constant coefficients if fd d is a non-homogeneous function of d and d dash. And we have seen that if fd d can be written as a product of linear factor of the form bd minus ad minus c, then the part of general solution corresponding to this type of linear factor is given by e raised to cx over b into some arbitrary function of by plus ax if coefficient of d, which is b, is non-zero, and if coefficient of b is 0, then this quantity is undefined. So in that case we will check whether coefficient of d dash is non-zero or not, and if coefficient of d dash is non-zero, then the general solution will be e raised to cy divided by a arbitrary function of by plus ax, and here if a is not equal to 0. And we have also discussed the case that if ad dash plus c is a linear factor of fd d, then the part of general solution corresponding to this type of linear factor is e raised to minus cy over a times arbitrary function of a into x, and this is valid if a is non-zero. So these things we have discussed in lecture number 6. Now in this lecture we are going to discuss the case of repeated linear factor of this form. Suppose we have this linear factor is repeated 2 times, then how to write down the part of general solution. Suppose I have fd d as a product of linear factor bd minus ad minus c, and it is repeated, then what will be the part of general solution corresponding to this product of 2 same linear factors. So for that we know that if we have this type of linear factor and if b is non-zero, then we have this part in the general solution e raised to cx over b, some arbitrary function say phi1 of by plus ax, and here also we have same type of same linear factor. So for that also we will write e raised to cx over b arbitrary function of by plus ax. But if we are writing in this way, then we can see that these two functions are not linearly independent. So to make them linearly independent, we will multiply at least one function by x, and if we take this e raised to cx over b common, then we have arbitrary function of by plus ax plus x times arbitrary function, another arbitrary function of by plus ax. Similarly, if we have this linear factor repeated 3 times bd minus ad minus c, then here we will multiply one more term, that is x square times some arbitrary function of by plus ax denoted by phi 3. So in general, if we have this type of linear factor which is repeated, and it is repeated say m times, then the part of general solution corresponding to this type of linear factor is given by e raised to cx by b arbitrary function say phi1 of by plus ax plus x times e raised to cx by b arbitrary function of by plus ax denoted by phi 2, and if here we have m power, then we have to keep multiplying up to x to the power m minus 1, and we will have m arbitrary functions of by plus ax, and there will be e raised to cx by b common in each term. Therefore we can rewrite this in this form also, e raised to cx over b phi1 plus x into phi 2 up to x raised to m minus 1. So we will remember that if we have repeated factor m times, then we will have m arbitrary functions of by plus ax, and we will keep multiplying up to x to the power this m minus 1, and this is valid if b is non-zero. But suppose b equal to 0, then we know that if b is 0 and a is non-zero, then we have this type of part in the general solution, e raised to minus cy over a arbitrary function of by plus ax. And if we have repeated linear factor, then we will here multiply by powers of y. So instead of x, now we have e raised to minus cy over a arbitrary function of by plus ax plus y times arbitrary function of by plus ax, and so on, y raised to m minus 1 arbitrary function of by plus ax if a is non-zero. And if b is non-zero, then here we have m arbitrary functions of by plus ax, but in multiplication we will write powers of x, and if a is non-zero, then in multiplication we will write powers of y. Similarly, if we have this type of linear factor a d dash plus c, if you recall, we have seen that corresponding to a d dash plus c, the part of general solution is e raised to minus cy over a arbitrary function of ax. Now suppose this is repeated 2 times, then we will write another same function e raised to minus cy over a another function of ax, but here we will multiply by y to make these two linearly independent. If I have mth power, then the part of general solution corresponding to this m times repeated factor a d dash plus c is e raised to minus cy over a arbitrary function, say phi1 of ax plus y times phi2 of ax up to y to the power m minus 1 arbitrary function of ax denoted by phi m. If I have m power here, I have to keep multiplying up to m minus 1th power of y. So this is easy to remember, and we now try to solve some problems which are based on this type of repeated linear factors. Here we are asked to solve this partial differential equation given by r plus 2s plus t plus 2p plus 2q plus z equal to 0. And we are familiar with all these notations. P means partial derivative of z with respect to x, q means partial derivative of z with respect to y, r means second order partial derivative of z with respect to x 2 times, and s means second order partial derivative of z with respect to x 1 time and with respect to y 1 time, and t is the notation for second order partial derivative of z with respect to y. So using these notations, we are able to write this equation in this form. And now if we use the notation that del z by del x is denoted by capital D, del z by del y is denoted by d dash, then this is nothing but d square plus 2 times d into d dash plus d dash square plus 2d plus 2d dash plus z equal to 0. So that I have written here. So this is our function of d and d dash, which we denote by capital F. And we can observe that this function is non-homogeneous in d and d dash. Here degree of this term is 1, this is also 1, here degree is 0, and in all these terms degree is 2. Therefore degree of each term is not same in this function of d and d dash, therefore it is non-homogeneous. So we will try to write this function as a product of linear factors. So for that we can observe that this is nothing but square of d and d plus d dash, d square plus 2 times d dash plus d dash square. From this also we can take 2 common, so we will have 2 times d plus d dash and plus 1. So that I have written here d plus d dash square plus 2 times d plus d dash plus 1, and this quantity is nothing but square of d plus d dash plus 1. If I take square of d plus d dash plus 1, then I will have d plus d dash square plus 2 times d plus d dash into 1 plus square of 1, which is 1. So again I can rewrite this as square of d plus d dash plus 1 into z equal to 0. So this is our function capital F in this equation, and we can see it is homogeneous function, and we have this it is not homogeneous function, it is reducible. We are able to write capital F as a product of two linear factors d plus d dash plus 1 and d plus d dash plus 1. So this is the case of repeated linear factors of the form bd minus a d dash minus c, and it is repeated 2 times, that is m equal to 2. Now for writing the general solution, first we have to compare this factor with bd minus a d dash minus c, and we can see that b is 1 and a is minus 1 and c is also minus 1. So here I have written that comparing d plus d dash plus 1 with bd minus a d dash minus c, b equal to 1, a equal to minus 1, because here d dash has coefficient 1, here d dash has coefficient minus a. This implies a equal to minus 1, and 1 equal to minus c, that gives me c equal to minus 1, and this is repeated 2 times. And here b is non-zero, so we will use this formula e raised to cx over b, arbitrary function of by plus ax. So one function will be denoted by phi 1, and because this is repeated 2 times, we will have to write x times e raised to cx by b, another arbitrary function of by plus ax denoted by phi 2. So what is c over b? C is minus 1 and b is 1, that is e raised to minus x. Phi 1 of by, b is 1, that is y, and a is minus 1, so it is y minus x. So therefore the general solution is e raised to minus x arbitrary function of y minus x plus x times arbitrary function of y minus x. Okay, here we can take e raised to cx over b common, and we are left with arbitrary function of by plus ax plus x times arbitrary function of by plus ax, and then we substitute these values of a, b and c, and we obtain that this is the general solution of given partial differential equation. I have taken another example to explain this fact, that suppose I have a d dash plus c as a repeated linear factor of capital F, then the part of general solution corresponding to this factor is e raised to minus cy over a, arbitrary function of ax plus y times another arbitrary function of ax, and because here m power, we have to keep multiplying up to m minus 1th power of y, and because I have m factors here, I have to write m arbitrary functions. So we can see here f d dash is d plus 3 square, and it is the factor of this form a d dash plus c raised to m, so that we can compare with a d dash plus c, and we obtain that a is 1, c is 3. Therefore general solution is e raised to minus cy over a, arbitrary function of ax plus y times another arbitrary function of ax. C is 3, a is 1, so we have 3 by 1, that is e raised to minus 3y, and a is 1, here we require value of a, so a is 1, that is phi 1 of x plus y times phi 2 of x, where phi 1 and phi 2 are arbitrary functions. So in this way we can easily solve homogeneous linear partial differential equations with constant coefficients. We have seen two types of differential equations which we can write in this form. In one type we have seen that FD itself is a homogeneous function of d and d dash. If FD is homogeneous in d and d dash, then we have seen the method for solving this type of equation. And if FD is non-homogeneous, then we have seen the method if FD is reducible into linear factors. If we can write FD as a product of linear factors, then we say that FD is reducible into linear factors. And if FD is reducible into linear factors, then we have seen the method for writing the general solution of this type of homogeneous linear PDE with constant coefficients. So from next lecture onwards, we will try to solve non-homogeneous linear PDEs with constant coefficients. So we will have some non-zero function of x and y on the right hand side, and for this the method is similar to the non-homogeneous linear ordinary differential equations with constant coefficients. If you recall, to solve the non-homogeneous linear ODEs with constant coefficients, we have to first find out the complementary function, and then we have to find out the particular solution or particular integral, and then general solution is the addition of complementary function and particular integral. This we have seen in the course of ordinary differential equations which are linear and with constant coefficients. So same theory we will have for non-homogeneous linear PDEs with constant coefficients, that we will start from next lecture onwards. So this is all about this session. I hope you like it. Thanks for watching.